In the summer of 1967, a pen scratched a thin black line across a roll of paper outside Cambridge. Most of the line was noise, tiny variations in radio energy gathered by an experimental telescope made from posts, wire, and a heroic amount of mud. Then, in one narrow strip, the ink changed. Not a picture of a star, not a clean spike, just a quarter-inch of untidy squiggle that occupied about 1 part in 10 million of everything the telescope had recorded. The person who noticed it was a 24-year-old graduate student named Jocelyn Bell. Her assignment was not to discover a new kind of star. She was supposed to study quasars, distant objects whose radio light flickered as it passed through the solar wind. But Bell had spent months learning the personality of those charts. She knew the ordinary static. She knew local interference. And this mark felt wrong in a way she could not yet explain. That instinct matters because the signal was not waiting in a polished graph. It was buried in paper. Hundreds of feet arrived every few days. Bell inspected it by eye, marking known sources and suspicious interference. The strange squiggle often vanished, but when it returned from the same place among the stars. On the 28th of November, a faster recorder finally caught the source clearly. The pen began drawing separate pulses, one after another, roughly 1 1/3 seconds apart, a clock in the sky. At first, that was almost worse than noise. Nature was not supposed to broadcast with such mechanical regularity. If the pulses were real, something unknown was turning the universe into a metronome. The machine that heard it hardly looked futuristic. Antony Hewish had designed the interplanetary scintillation array to study compact radio sources. Building it required a field covering several acres, more than 1,000 posts, and roughly 120 miles of wire. Bell helped drive posts, string cables, and solder connections. Then she became the person who lived with its output. The array watched radio sources twinkle. Visible stars seem to twinkle because moving air bends their light. Compact radio sources can twinkle when their signals cross turbulent plasma carried by the sun. Hewish wanted to use that effect to identify quasars. The telescope converted changing radio power into moving ink. Bell's job was to separate the sky from every tractor, radio transmitter, electrical fault, and human-made disturbance that could imitate it. This is why the discovery was not a lucky glance. Bell had built an internal catalog of mistakes. Local interference appeared at the wrong time. Equipment faults did not follow the stars. The new signal did. Day after day, it arrived about 4 minutes earlier by the clock, exactly what a fixed celestial source should do as Earth moved relative to the stars. Hewish remained cautious. Perhaps Bell had wired something incorrectly. They arranged a check with another telescope. Her instrument showed the pulses, but the second recorder stayed flat. For a few terrible minutes, the discovery seemed to collapse. Then the pulses appeared. The team had miscalculated when the second telescope would see the source. The sky had answered twice. But a celestial source created a stranger question. What in the sky could send a pulse every 1.337 seconds with that precision? A normal star was far too large to change so quickly as a whole. A planet reflecting radio waves would not behave like this. An orbiting pair of objects would need an implausibly tight dance. The group checked clocks, receivers, and the possibility of signals bouncing from the moon. They also gave the source an internal nickname, LGM, for Little Green Men. It was a joke with an uncomfortable edge. A narrow, regular signal was exactly the kind of thing people imagined an extraterrestrial transmitter might produce. The team did not announce aliens. They tested the idea by asking what an engineered beacon should do, and whether the signal carried modulation or planetary motion. Then Bell found another pulsing source in a different part of the sky. And another, and another. 4 independent civilizations choosing the same transmission style at the same moment was not a serious explanation. The multiplication of the mystery killed the alien story and strengthened the astronomical one. This was a class of object. The pulses differed, but each source behaved like a compact celestial clock. The team called them pulsating radio sources, quickly shortened to pulsars. The name described the observation without pretending they knew the engine. Now physics had to invent an object small enough to pulse quickly, massive enough to release enormous energy, and stable enough to keep time across interstellar distance. The answer had been imagined decades earlier, a neutron star. When a massive star exhausts the fuel supporting its core, gravity wins. The core collapses. Under crushing pressure, electrons and protons are driven together, leaving matter dominated by neutrons. A mass comparable to the Sun can be packed into a sphere only tens of kilometers across. Collapse also transforms motion. Pull your arms inward while spinning and you rotate faster. A stellar core does the same on a scale that barely fits inside the imagination. Its radius shrinks by orders of magnitude, so a slow stellar rotation can become a turn every second, or even many turns each second. The magnetic field is compressed and intensified at the same time. A pulsar is not a lamp blinking on and off, it is closer to a lighthouse. The neutron star's magnetic axis is tilted away from its spin axis. Charged particles accelerate around the magnetic poles and produce beams of radiation. As the star rotates, those beams sweep across space. Earth hears a pulse only when a beam crosses our line of sight. That geometry explains the regularity. The star supplies the clock. Rotation supplies the sweep. The narrow beam supplies the flash. Most neutron stars will never pulse toward us because their beams miss Earth. The ones aligned with us turn a dead stellar core into one of nature's finest clocks. Bell's ink marks were the shadow of an object spinning across a gulf of light years. The Cambridge Group published the discovery in February 1968 with 5 authors. Antony Hewish was first author. Jocelyn Bell was second. The cautious paper described a rapidly pulsating radio source and worked through possible explanations. Within months, observations connected pulsars with supernova remnants, especially the Crab Nebula, where a stellar explosion had been recorded in the year 1054. The connection made physical sense. A supernova could leave a collapsed neutron core. The Crab pulsar turned about 30 times each second and flashed in radio, visible light, and X-rays. The new objects were not merely clocks, they were laboratories containing densities and magnetic fields no experiment on Earth could reproduce. Pulsars also refuse to be perfectly simple. They gradually slow as they radiate energy. Some suddenly glitch, spinning a little faster before resuming their long decline. Some orbit companion stars. Timing those systems lets astronomers test gravity with extraordinary precision. One binary pulsar later supplied indirect evidence for gravitational waves because its orbit shrank at the rate predicted by general relativity. Millisecond pulsars rotate hundreds of times per second after being spun up by material from a companion. Networks of these objects can act like a galaxy-sized detector, sensitive to subtle distortions in space-time. A quarter-inch of unexplained ink opened routes into stellar death, nuclear matter, magnetic fields, navigation, and gravity. In 1974, the Nobel Prize in Physics went to Martin Ryle and Antony Hewish. Ryle was honored for radio astronomy observations and aperture synthesis. Hewish was cited for his decisive role in the discovery of pulsars. Jocelyn Bell Burnell was not included. That fact is easy to compress into a clean villain story, but the history deserves more care. Hewish conceived and led the telescope project. The instrument and Cambridge radio astronomy program were major achievements. Bell Burnell was also not a replaceable pair of hands. She helped build the array, examined the charts, recognized the anomalous source, recovered its earlier appearances, and persisted until the pulses were undeniable. Bell Burnell has often described the omission without presenting herself as a stolen genius. At the time, major awards commonly followed the senior scientist rather than the graduate student. That convention explains the culture. It does not make her contribution disappear. Later institutions increasingly described her as responsible for, pivotal to, or the discoverer of pulsars. The honest tension is more interesting than a manufactured theft. Science needs large projects and leadership. It also depends on the person close enough to the evidence to notice when reality refuses to follow the plan. Recognition systems often prefer a hierarchy. Discovery itself does not care about rank. It appears wherever someone has learned the data well enough to see the one mark that does not belong. Bell Burnell went on to work across radio, gamma ray, X-ray, infrared, and millimeter astronomy. She led scientific organizations and became an influential teacher and advocate. In 2018, the Special Breakthrough Prize recognized her fundamental contribution to discovering pulsars and awarded her $3 million. She chose not to keep it. The money was directed towards scholarships for people underrepresented in physics. The decision connected the beginning of her story to its later meaning. A student once working at the edge of an academic hierarchy used belated recognition to bring more students through the door. Today, pulsars keep time across the galaxy. Their beams cross Earth with messages about collapsed stars, extreme matter, and warped spacetime. But the first message was quieter. It was a tiny irregular patch on an ocean of paper, noticed because one person had taken the supposedly routine work seriously. Jocelyn Bell Burnell did not set out to find a cosmic lighthouse. She learned the noise so completely that the universe could not hide one from her. If you want more stories about the people who noticed what everyone else passed over, subscribe here on the board, and tell me in the comments whose evidence we should follow next.